Reedon is a consulting firm specializing in innovation and product development using virtual testing. Our team of innovation experts has diverse backgrounds in mechanics, thermodynamics, fluid dynamics, and acoustics. With a collective experience of over 20 years in addressing innovation challenges, we are dedicated to delivering the solutions our clients need. Our guiding principle is, before trial and error, let's do the physics first. With this mindset, we provide tools to solve engineering problems. Our deliverables range from feasible product designs, conceptual models, and feasibility studies to functional mock-up units, digital twins, and customized software solutions. As part of the EMOCO project, we are developing a digital twin framework that integrates a virtual model with real-time information from the physical counterpart. A crucial element in digital twins is a reduced-order model. Such a model helps capture the key behavior of the problem while leaving out complex details that can make the model computationally expensive. In this presentation, we'll explain how to create and use such a model. In this project, we are focusing on a conveyor belt oven process, which is a typical production process in industry. From hardening of steel to the baking of cookies. Typically, there is a trade-off between the throughput and the quality. Placing more product on the belt increases the throughput, but will all products experience the same temperature trajectory as they move through the oven? The quality of the product is closely tied to the temperature experienced. To address this question, we use what we call a virtual temperature sensor. A model of the thermal process is made and used to predict the temperature of the product for a given situation. This model is used in a practical use case where we want to know how to position parts to ensure low temperature variability in a conveyor belt oven process. Every model begins by pinpointing the relevant physics. In each thermal process, three primary forms of heat transfer come into play: radiation, convection, and conduction. As depicted, the heat source, in this case, the campfire, emits heat through radiation, a sensation you can feel even at a distance. The heat source generates hot gases that undergo convection, noticeable when placing your hands in the upward flow of these hot gases. Additionally, heat can traverse through a solid object via conduction, an experience akin to holding a poker in the fire. Within the oven, the temperature-controlled walls serve as the heat source, facilitating the transport of heat to the product along various pathways. The oven heats the part directly via radiation, but also the belt is heated. There can also be radiative heat exchange between parts and between a part and the belt. Conduction takes place within the part and within the belt. Since the part and belt are in close contact, there is also conductive heat transport between part and belt. Furthermore, there can be convective heat transport between the oven medium, usually a shielding gas, and the products. To assess the significance of different transport phenomena, we estimate their order of magnitude. We evaluate the heat conductance or heat transfer coefficient for each phenomenon at typical temperatures. Forced convection is disregarded due to the limited flow of shielding gas. In the case of natural convection, resulting from local temperature variations in the medium, the heat transfer coefficient falls between 10 and 25, considerably smaller than the 343 observed for radiation. Concerning transport between the part and the belt, conduction emerges as the predominant phenomenon, with a value of 755 watts per square meter Kelvin. In summary, we predominantly rely on conduction within a part. Between the oven wall and the part, as well as between the wall and the belt, we utilize radiation. Radiation is also considered between parts. When it comes to transport between the belt and the part, we employ conduction through stagnant shielding gas. It has been found that the chain geometry and the placement of the part relative to the chains has no significant effect on the heating of the part. The left image shows the radiative heat flux on the bottom of the part. In blue, the shadows of the chains can be recognized. Although there exists variation in the radiative heat flux on the bottom, such variation is not present in the temperature field, as shown on the right. Inclusion of all the geometric details of the individual chains is too expensive for a parametric study where the placement of the parts relative to each other is studied. To cope with this issue, a simpler description of the belt is required. We make a simpler model of the conveyor belt in two steps. First, we use a basic unit cell to represent the belt. This unit cell includes a small part of the belt with a part on top, shown in red. The oven walls are depicted above and below in white. Using simulation software Abacus, we simulate the heating of this small section both with and without the part. We use proper periodic boundaries in the simulation. In the second step, we simplify the geometry even more to create a bulk model. Here, the belt is modeled as a solid with the same heat capacity, but we adjust the transport properties to achieve the same thermal response. In the simplified model, the belt is divided into two parts. This helps us make the belt partially transparent, enabling radiative heat transfer between the oven wall and the middle surface. If there's a part above the belt, the part gets heat from the oven wall. When there's no part, the top of the belt gets heated directly by the oven wall. We use a heat conductance between the belt and the part to represent how well heat travels between the two. The heat moving through the belt is modeled with an anisotropic thermal conductivity, meaning it conducts heat differently in different directions. This slide summarizes the tuning of the parameters of the bulk model. The table on the right explains different parameters and shows the values that worked best, providing the closest match between the unit cell and bulk model. The graphs at the bottom display the temperature response for both models in two scenarios, with and without the part. We're looking at how the temperature changes when a piece of belt is suddenly placed in the oven at 1000 Kelvin at T=0. In the graph showing the difference between the two models, we observe that the bulk model does a good job capturing the average temperature. It also does well with the temperature range, min and max, for the part. Although the temperature range for the belt isn't as accurately captured, it's considered less critical since our main focus is on accurately describing the part. Next step in creating the virtual temperature sensor involves constructing a parametric model, utilizing the simplified belt description. In this study, a simplified arrangement is used, in which the parts are consistently arranged in a hexagonal pattern resembling the standard production topology, yet not all parts share the same configuration of neighboring parts. For instance, a part located near the edge may have only 3 neighbors, whereas, in most cases, a part will have 6 neighbors. There is also the possibility of vacant spots if the supply is interrupted. A parametric investigation is conducted, simulating all potential neighbor configurations at various separation distances. To conduct a parametric study in Abacus, it's typically helpful to develop a script or function that outlines the simulation model for a particular set of parameters. In this study, I utilized a function called construct_geometry, which requires 2 inputs, a label for the neighbor configuration and a separation value. The function executes a series of steps to construct the model. Firstly, it generates a belt unit cell in the shape of a hexagon based on the provided separation. This hexagon is then used to create both the upper and lower sections of the belt. Afterward, the function establishes a pattern for the given neighbor configuration, adding parts to specific adjacent hexagon tiles. The subsequent actions involve merging the various hexagon tiles into a single part, assigning material properties, and defining the interactions related to heat transport. Calling this function for configuration 4 and a separation of 40 mm would appear like this. Once a simulation is completed, we need to extract the relevant data. In this scenario, we focus on the average temperature of the central part. Additionally, we examine the temperature difference within the part itself. We run a simulation for every combination of 13 potential neighbor setups and 10 various separations. To analyze the results, we use a neural network to describe the response surface, providing a quick and smooth evaluation between simulated data points. While linear interpolation could achieve this, a neural network is chosen to showcase its capabilities. Neural networks are effective in modeling intricate and nonlinear response surfaces, making them suitable for complex relationships or numerous input factors. However, the choice should consider trade-offs, as neural networks have challenges like interpretability and require careful tuning, whereas interpolation tables may be sufficient for simpler relationships and well-understood input spaces. Nowadays, user-friendly frameworks like PyTorch make it easy to apply neural networks to your data. To further explore the results, we define key performance indicators. We use the maximum temperature difference compared to a reference scenario, a single part without neighbors, and the highest temperature difference within a part to determine an acceptable operating range for how closely parts can be placed on the conveyor belt. To easily visualize and explore the results, we use Reeves DSE, which stands for Reeves Design Space Exploration. A model build in Reeves DSE serves as a knowledge bank and an application engine in one. It allows you to document and update your knowledge, while at the same time applying that knowledge for research and development purposes. In this short demo I will show how knowledge is documented and how we can find a suitable operating windows for placement of caps on the conveyor belt. In the knowledge view we see 3 sections. This first section documents the belt description similar as we discussed here. The second section provides the background information about the parametric simulation performed in Abacus. This third section defines the knowledge rules used by the model. For example, the input configuration label can be defined by the number of neighbors and the measure of spread. This mapping is stored in a lookup table. The DOE output for the KPIs is stored in an interpolation table, while a Python function call is used to get the time-dependent response from the neural network. Now we switch to the calculation mode, and we start with an empty model. First thing we need to do is generate solutions. To fill the space we use a value of 1000 solution, hit the play button and wait. It is ready. Now, each dot in a graph is a solution for a particular configuration. In the top left graph, you can see the different discrete neighbor configurations. When selecting this solution with 3 neighbors and a high spread, the right graph visualizes the configuration. Let's focus only on this neighbor configuration. By selecting Keep, we remove all other points. In this figure we can now vary the separation. The graphs in the middle show both KPIs. For a large separation they are both low, but for small separations there is quite some variation. Now let's try to identify the operating window for the separation where all neighbor configurations result in both KPIs below 20 degrees Celsius. First include all solutions. Then, select all points with max difference above 20 degrees Celsius. Add all points to the selection with a max local temperature difference above 20 degrees Celsius. You do this by holding Shift while selecting. In this graph you can see that if we place the caps at least 40 mm apart, both KPIs are below the 20 degrees Celsius for all possible neighbor configurations. You can further explore the results yourself by downloading Reeves DSE for free and get the model from our website. In summary, we began by addressing a practical optimization question from the industry. Firstly, we pinpointed the relevant transport phenomena. Secondly, we created a simplified model of the conveyor belt, considering its detailed geometry. Next, we conducted a parametric study using a model that incorporates the pertinent physics. Finally, we utilized Reeves DSE to visualize and filter the results, allowing us to answer the key question regarding how closely we can pack products on the conveyor belt without compromising quality. Up to this point, we've utilized the virtual temperature sensor as a design tool to improve a production process. The next step is to apply it in real-time production. The data from the virtual temperature sensor can be linked to each specific product, allowing for the identification of correlations with other aspects observed during quality control. We conclude this story by examining some experimental data where this approach was implemented. A set of experiments was conducted where different parts with various neighbor configurations were placed on the conveyor belt. For each part, we recorded the separation and neighbor setup, obtaining a virtual temperature signal. After the heat treatment, we measured a critical to quality dimension. Using the 2 previously defined KPIs, we can now investigate potential correlations. In the graphs, the measurement data is plotted against the 2 KPIs. It is clear that there is a strong correlation with the maximum difference in average part temperature compared to the reference, with a correlation coefficient of 0.96. For the second KPI, the maximum local temperature difference within a part, there is no clear correlation observed, as the correlation coefficient is -0.23. It appears that the change in average temperature is more crucial than local temperature fluctuations when it comes to the measured dimension. Thank you for your attention. If you have any questions, feel free to contact us.